Hello class, so this is mostly going to be on magnetic flux and Faraday's law, as in know how to solve problems using both equations, and hopefully in a general way you'll understand more what flux is. Also, we're going to start talking about our solar oven project and going over part A for all of you seniors or anyone who's sick on Monday. I'm going to say a lot more on this part than I'm going to write, so be sure to listen carefully. So first off, I want to go over our laws. So to find flux, or magnetic flux, remember phi is our magnetic flux, and it is measured in WB, or Webers. B is our magnetic field, measured in Teslas. Sorry about that. So remember, B is our magnetic field, measured in Teslas. A is our area. So this throws a lot of people off because it could be a couple different things. If it's a square, you want to multiply your length times your height. If it's a circle, it is pi r squared. And remember, this must ultimately be in meters squared, so make sure you change your units to meters. And then cosine. Cosine, at least to find the theta, you're measuring how far away it is from the perpendicular. So remember, if it's flux perpendicular, things are going in perfectly. So this is the angle you want. You're not looking for the angle on this side. So if it is perpendicular, your angle would be 0 instead of your standard 90, because we're talking about how far away it is from perpendicular. If it's perpendicular, you are 0 degrees away from it. Alright, then the next one, using this equation, you can find your voltage. Remember, your volts, or voltage, is measured in volts. Easy unit to remember. This is going to be your final magnetic field minus your initial magnetic field. So you need at least two, or magnetic fluxes, excuse me, but initial flux from that and minus the final flux over your change in time. Often this is just given as one number, and that's fine. You would just say it starts at 0 and you would subtract 0 from it. Again, these are, let me fix that for you guys. These are measured in Webers. And then T is, of course, measured in seconds. Alright, so we're going to do some practice problems together. Again, be sure to try them, and then come back to see the full solved answer. Alright, so I know we've probably already done this page in class, or hopefully you have, but go over 1, 3, and 5 are what I'm going to go over today, with a particular focus on 5, because I think it is the hardest one on this page, and it encompasses everything. Alright, so go ahead, try it, and then come back. Alright, now that you've tried it, I'm going to specifically focus on just 1 and 3. So for 1, again, first thing, always read it. So we have a 9.2 centimeter diameter circular loop is oriented perpendicular to a 1.5 Tesla magnetic field. What is the magnetic flux for the loop? So especially while you're still getting used to these, you should always draw a picture. So we have a loop that is perpendicular to a 1.5 Tesla field. Remember, that is your B. Its diameter is 9.2 centimeters. This is unuseful in a lot of ways. We'll need to find the area of this, and for that we need the radius, so we can do pi r squared. But the diameter is not the radius, so we first have to put it into meters. And the radius is worth half of that. So that's how you find your radius. And then from there, you can plug all of this into your equation. Remember, that is phi is equal to BA cosine theta. B is 1.5 from the problem. A is pi r, which we found by 0.046, and then you're going to square that. Then you're going to multiply by your cosine theta. In this case, your angle off the perpendicular is 0 because it is perfectly perpendicular. If you saw 0.00997, or you could have rounded to 0.01, or it could have been 9.97 times 10 to the negative third. Either works. Either way, this is a number we're definitely going to want to know for number 3. So number 3 is the same, except we're trying to find the voltage, but we are still using this loop. Remember, I'm skipping 2. So our initial flux in this case is going to be 9.97 times 10 to the negative third. So we need to figure out what our final flux is so that we can find our voltage. And we do have time. It is 0.1 seconds. So if the loop in question number 1 is rotated so that is parallel to the magnetic field, if this takes 0.1 seconds, find the voltage induced in the loop, or induced also means created. So it's the idea that we had this loop, and then it rotated to look like this. So hopefully looking at this you might think, well, there's nothing going through it. Absolutely. Your total flux at the end is 0. So you would get 0 minus your 9.97 times 10 to the negative third over 0.1. If you solve this, remember it's going to be positive. You should get 9.97 times 10 to the negative second, or 0.0997. Alright, I am going to erase this page and dive into 5. So number 1 and 3 broke it up piecewise, but 5 is just all of it all at once. You will absolutely need both of these equations and this one to find your voltage. So first off, you will need to do this twice, depending on how you do it. So always just set up your equations first. So we know there's some initial or final B, A cosine theta minus, because remember this we're subtracting here, from some other B, A cosine theta. So if nothing changed, your voltage would be 0, which makes sense. If there is no change, there is no voltage over your time. So this is where we want to start looking at what we have. So we have a 6.5 centimeter field, or 0.065 meter on each side. That means the other side, because it's a square, is also the same. And it consists of 275 loops. So for each loop, you are going to get more voltage, because the more loops, the more. Alright, so then you can find the area, or actually I'd best just to plug in for these. So B in this case is 0.5 later. And then in the beginning, it was 2.0. So there's 2 ways you could do this. You could let yourself know that some of these are the same and take them out, or you can leave them in. Either way would work. Personally, I like to leave them in, but that is just me. So 0.65 squared for your area. And then since they are also perpendicular, you keep your cosine of 0. And you would subtract, now your field is 2, still times 0.65 squared times cosine of 0. Sorry, that got messy. Okay. You could plug this straight into your calculator, depending on the calculator you have. So that's what I am going to do. And then you would divide by 0.05 seconds. So then you just plug this into a calculator. Alright, so you should get negative 0.12675, but if you do the absolute value, then remember, this is per coil. So you want to multiply by how many loops they are, because the more loops, the more energy you can get. And so it should be 34.9 with rounding. Alright, hopefully this was informative. If you have A done, go ahead, log off, see you later, have a good weekend, or afternoon, no weekend yet. If not, please stick around to talking about solar ovens. So, what we went over yesterday was mostly solar ovens. How do they work macroscopically and microscopically? So this would be on your first couple of pages. So we did kind of talk about this today, about the idea that some sort of light goes in, we have some sort of energy go out. I'm not going to talk about that as much because I'm not going to do it for you, but I do want to go over what each part means. So looking at this page, I believe this is page 2. So you should draw a model of a solar oven. So you should sketch both macroscopically and microscopically. So you should have some idea of magnitude and direction. You don't need exact numbers, but you should show maybe the size of the energy with how big your arrows are. So which energy goes in, which energy goes out, and your energy transformations. And if there's any movements of molecules or matter within or between the oven and surrounding, and hopefully show that all energy is conserved. That would be right here. Then below it, there's a place for you to summarize and explain it. Make sure you're using labels and arrows while you are drawing. So microscopically, same thing, but you're looking at the inside of your oven walls. So this is where I drew my particles. To again show the transformation of solar energy to thermal energy, include changes that talk about your molecular motion, and identify the features of the surface that maximize the transformation. So how can you make sure that as much energy as possible, because remember, light can bounce off things, but you want as much of it to be absorbed. So what are you going to do to make sure of that? And then illustrate the changes in types. So if you have not done that, please go and do that. That would be the first 2 pages. And then secondly, let's clear off. Secondly, we want to talk about some features of your design. So these would be your design factors. So things that you want to look for in your design. There's a lot of things to think about. First of all, you do have to consider your material. What are you going to use? How are you going to use it? Then you should also think, how thick are your walls going to be? Also, how large is your opening? Your opening size is going to determine how much sunlight gets in. Do you want to minimize or maximize this, and how can you? Also, you want to think about is your shaded areas. Without it in a 3D object, there's no way to avoid shading, even if it's just the bottom of the box. So your shaded areas are going to have no sunlight. And this is also your areas where you can lose your heat. Also, with the material, you should definitely think about what color it is. If you've ever stopped out in the sun in a white shirt versus a black shirt, you probably know which one makes you warmer. This is also going to be a factor. You also should think of the overall just area of your box, so your size, volume, etc. How big is your box going to be? And just keep thinking about how do you want these things to change for your box. What's going to happen to it? What's it going to look like? Later, we're going to start talking about reflectors and the roles that they play. But your first box will have no reflectors in the beginning. Ultimately it will, because as many of you, if you've ever seen one, reflectors can be very important. If you're still not sure what a reflector looks like, you should Google solar box oven. This should give you an idea of what some look like. Hopefully this was informative, and have a good afternoon.